Hi students, I am Sheeba, ECE department from Emmanuel Arasar JJ College of Engineering. Today we are learn about the topic operational amplifier. These are the diagram of operational amplifier ICs. The operational amplifier was introduced in the year 1947. Next, we can see the operational amplifier introduction. The short form of operational amplifier is OP-amp. Operational amplifier is fundamentally a voltage amplifying device. It gives high gain and high input resistance RIN. It is directly coupled negative feedback amplifier. The amplifier can perform a variety of mathematical operations like addition, subtraction, multiplication, differentiation, and integration, etc. in analog computers. That is why it is named as operational amplifier. It has scales changing analog computers operations, instrumentation and control systems, phase shift and accelerated circuits. The feedback components determine the resulting function or operation of the amplifier. The different feedback configurations of resistive, capacitive or both types can be used in operational amplifier circuits. Next, we can see the different types of operational amplifier. The most common operational amplifier is the 741 IC. It has three packaging types. First one is 8 pins DAP package. It is used in operational amplifier 741 type. Next one DAP SMT package. Third one TO 5 metal can 8 LEDs package. Next, the diagram of different older versions of operational amplifier. Next, we can see the examples of operational amplifier. First type is New A709 Semiconductors Limited, Pune. It is the high gain operational amplifier constructed on a single chip. It is mainly used for DC servo systems, high impedance analog computers, and low level instrumentation applications. Next one is LM108, LM208 Semiconductors Limited, Mumbai. Third one is CA741 CT, CA741T Bharat Electronics Limited, Bangalore. It is the high gain operational amplifier. It is mainly used for comparator, integrator, differentiator, summer, DC amplifier, multi-vibrator, band pass filter. Next, we can see the operational amplifier ID code. For LM741CN, the prefix is LM, designator type is 741C, the suffix is N. The prefix AD bar OP denote the manufacturer is Analog Devices. CA for Kaitse means Harish. KA means Fairchild. LM means National Semiconductor. MC means on semiconductor. NE bar SC means Signetics. OPA means Burr Brown. RC bar RM means Raytheon. SG means Silicon General. TA means Texas Instruments. The code application and temperature. C denotes the application is commercial application and the temperature is 0 to 70 degrees Celsius. I means industrial application and the temperature is minus 25 to 85 degrees Celsius. M means military application and the temperature is minus 55 to 125 degrees Celsius. And the code package type D, VD means surface mount package. J means ceramic dual in line package. N, P, VP means plastic DIP. DM means micro SMP. Next we can see the operational amplifier symbol and pin configurations. Operational amplifier are drawn as a triangle in a circuit schematic. These are the symbol of operational amplifier. It has 2 inputs and 1 output, 8 pins. First, the inputs are inverting input and non-inverting input and 1 output. It is a multi-terminal device. It is internally quite complex. It has 2 input terminals and 1 output terminal. The terminal negative is inverting terminal and the terminal positive is non-inverting terminal. In 3 packages, this operational amplifier is available. First one, metal can package. Second one, the dual in line package. Third one, the flat package. Operational amplifier packages may have single, 2 or 4 operational amplifier. Typical packages have either 8 or 10 or 14 terminals. The widely used very popular type MU-A741 is a single operational amplifier and is available as an 8-pin CAN, 8-pin DAP or 10-pin flat pack or 14-pin DAP. There are 5 basic terminals. First one is 2 input terminals. Second one is 1 input output terminal. Third one is 2 power supply terminals. V positive connected to positive terminal of 1 power supply. V negative connected to negative terminal of the other power supply. Both the common terminal of V positive and V negative is connected to ground. Usually plus or minus 15 volt is given to IC. The common point of the 2 supplies must be grounded, otherwise twice the supply voltage will get applied and it may damage the operational amplifier. Instead of using 2 power supplies, one can use a single power supply to obtain plus 15 volt and minus 15 volt by using the below given circuit. The next diagram is pin diagram of IC741. The first pin denotes the DC offset value and the second pin is 1 input inverting input and the third pin is denote the non-inverting input and the fourth pin is used for voltage negative and the fifth pin is used for DC offset and the sixth pin is output pin and the seventh pin is V positive. 8th pin give no connection. Next, we can see the block diagram of IC741. The first stage is current mirror stage, that is, it is the input stage. The input stage provides high input impedance to prevent loading on the high gain stage. It requires two input terminals. It also requires low output impedance. All such requirements are achieved by using the dual input balanced output differential amplifier as the input stage. The function of a differential amplifier is to amplify the difference between the two input signals. The differential amplifier has high input impedance. This stage provides most of the voltage gain of the amplifier. The next stage is intermediate stage, that is differential amplifier, and the third stage is class A gain stage. The output of the input stage drives the next stage, which is an intermediate stage. This is another differential amplifier with dual input unbalanced, that is single-ended output. The overall gain requirement of the operational amplifier is very high. The input stage alone cannot provide such a high gain. The main function of the intermediate stage is to provide an additional voltage gain required. Practically, the intermediate stage is not a single amplifier but the chain of cascaded amplifiers called multi-stage amplifiers. The next stage is level shifting stage. As the operational amplifier amplifies DC signals also, the coupling capacitors are not used to cascade the stages. Hence, the DC quotient voltage level of previous stage gets applied as the input to the next stage. Hence, stage by stage, DC level increases well above ground potential. Such a high DC voltage level may drive the transistors into saturation. This further may cause distortion in the output due to clipping. This may limit the maximum AC output voltage swing without any distortion. Hence, before the output stage, it is necessary to bring such a high DC voltage level to 0 volts with respect to ground. The level shifter stage brings the DC level down to ground potential when no signal is applied at the input terminals. Then the signal is given to the last stage, which is the output stage. The buffer is usually an emitter follower whose input impedance is very high. This prevents loading of the high gain stage. The last stage is output stage. The output stage is designed to provide low input impedance, large AC output voltage swing, and high current sourcing and sinking capability. The push-pull complementary amplifier meets all these requirements and hence used as an output stage. This stage increases the output stage swing and keeps the voltage swing symmetrical with respect to ground. The stage raises the current supplying capability of the operational amplifier. Next, we can see the two-stage architecture. It has four stages: input stage, intermediate stage, level shifting circuit, and output amplifier. The basic requirements of the input stage of operational amplifier are high voltage gain, high input impedance, two input terminals, small input offset voltage, small input offset current, high CMRR. CMRR means common mode rejection ratio, low input bias current. It provides the two input terminals, inverting and non-inverting terminal. The next stage is intermediate stage. The output of the input stage drives the next stage, which is an intermediate stage. The last stage is output stage. The function of the last stage, that is the output stage, is to supply load currents and provides low output impedance. The requirements of good output stage are large output voltage swing capability, large output current swing capability, low output impedance, low quotient power dissipation, short circuit protection. Next, we can see the equivalent circuit of IC 741. It has two input signals V2 and V1 applied to input terminal and another one input terminal respectively. The V2 is applied to negative input terminal and the V1 is applied to positive input terminal. This operational amplifier is said to be ideal if it has the following characteristics: open loop voltage gain equal to AOL equal to infinity, input impedance Ri equal to infinity, output impedance R0 equal to infinity, bandwidth BW equal to infinity, zero offset B0 equal to 0 when B1 equal to B2 equal to 0. It can be seen that first point, an ideal operational amplifier draws no current at both the input terminals, that is I1 equal to I2 equal to 0. Because of infinite input impedance, any signal source can drive it and there is no loading on the proceeding driver stage. The next one is, since gain is infinite, the voltage between the inverting and non-inverting terminals, that is differential output voltage Vd equal to V1 minus V2, is essentially 0 for finite output voltage V0. The third point is, the output voltage V0 is independent of the current drawn from the output, as R0 equal to 0. Thus the output can drive infinite number of other devices. A physical amplifier is not an ideal one, so the equivalent circuit of the operational amplifier is shown in figure. Here AOL is not equal to infinitive, Ri not equal to infinitive, and R0 not equal to 0. Note that AOL VD is there in equivalent voltage source and R0 is the Thevenin equivalent impedance looking back into the output terminal of operational amplifier. The output voltage is V0 equal to AOL into VD equal to AOL into V1 minus V2, that is VD equal to V1 minus V2. The equation shows that the operational amplifier amplifies the difference between the two input voltages. Next, we can see the ideal operational amplifier. The ideal operational amplifier has infinite voltage gain, AV equal to infinity. The voltage difference at the two inputs is magnified infinitely. In truth, something like 10 power 6. It means difference between positive terminal and negative terminal is amplified by 2 lakhs voltage. Second one, infinite input resistance Rn equal to infinity. No, it has no current flows into inputs. In truth, about 10 power 12 ohm for FET input operational amplifier. FET is field effect transistor. The ideal operational amplifier is a voltage controlled device. CAD 1 0 output resistance R0 equal to 0 ohm. Rock solid independent of load. It roughly true up to current maximum, that is 5 to 25 milliampere. 4 point, infinitely fast, that is infinite bandwidth. In truth, limited to few megahertz range. Slew rate limited to 0.5 to 20 volt per microseconds. Next, the rules of operational amplifier. When an operational amplifier is configured in any negative feedback arrangement, it will obey the following two rules. The inputs to the operational amplifier draw or source no current, that is whether negative feedback or not. The operational amplifier output will do whatever it can to make the voltage difference between the two inputs zero. Next, the operational amplifier without feedback. Without feedback means open loop configuration of operational amplifier. The internal operational amplifier formula is B out equal to gain into V positive minus V negative. So, if V positive is greater than V negative, the output goes positive. If V negative is greater than V positive, the output goes negative. A gain of 2 lakhs makes this device practically useless. Next one is infinite gain in negative feedback. Negative feedback means closed loop configuration of operational amplifier. Infinite gain would be useless except in the self-regulated negative feedback. Negative feedback seems bad and positive good, but in electronics, positive feedback means run away or acceleration, and negative feedback leads to stability. Imagine hooking the output to the inverting terminal. If the output is less than Vin, it shorts positive. If the output is greater than Vin, it shoots negative. Result is that output quickly forces itself to be exactly Vin. Figure shows the negative feedback loop. Next, the operational amplifier even under load. Even if we load the output, the operational amplifier will do everything it can within its current limitations to drive the output until the inverting input reaches Vin. Negative feedback makes it self-correcting. In this case, the operational amplifier drives a current through the load until the output equals Vin. So, what we have here is a buffer can apply Vin to a load without burdening the source of Vin with any current. The important note is operational amplifier output terminal sources were sinks current at will, not like inputs that have no current flow. Next one is positive feedback pathology. In the configuration below, if the positive input is even a smidge higher than Vin, the output goes way positive. This makes the positive terminal even more positive than Vin, making the situation worse. This system will immediately rail at the supply voltage. Figure shows the positive feedback, that is, the output is connected to the positive terminal of operational amplifier. Next one is virtual ground and summing point. Operational amplifier employs negative feedback with the help of resistor RF. Input and feedback currents algebraically added at point A, that is summing point. Virtual ground arises from the fact input voltage Vi at the inverting terminal of the operational amplifier. Point A is essentially ground voltage and referred as virtual ground. Why Va is reduced to almost zero. When V1 applied, negative feedback produces output voltage V0, which is opposite phase with input. The algebraic sum of the two voltages V1 and V0 becomes nearly Va equal to 0. This happens only when output V0 is exactly same and opposite equal of V1. If no current flows through the input, I equal to 0 means also Va is nearly 0. Next, the applications of operational amplifier. First one is linear amplifier. In these two applications, inverting amplifier are negative scale, non-inverting amplifier are positive scalar. Next one, unity follower, adder or summer, subtractor, integrator, differentiator, comparator. Next, inverting amplifier. These are the one application of operational amplifier. Figure shows the inverting amplifier. It is mostly used of all the operational amplifier circuits. It is also termed as phase shifting circuit. The output voltage V out is fed back to the inverting input terminal through R2 minus R1 network, where R2 is the feedback resistor. Input signal V in is applied to the inverting input terminal through R1 and non-inverting input terminal of operational amplifier is grounded. Applying the rules, negative terminal at virtual ground. So current through R1 is IF equal to V in divided by R1. Current does not flow into operational amplifier. So the current through R1 must go through R2. Voltage drop across R2 is then IF R2 equal to V in into R2 by R1. So V out equal to 0 minus V in into R2 by R1 equal to minus V in into R2 by R1. Thus, we amplify V in by factor minus R2 by R1. The negative sign ends title inverting amplifier. Current is drawn into operational amplifier output terminal. The negative sign indicates a phase shift of 180 degree between V1 and V out. Also, since inverting input terminal is at virtual ground, the effective input impedance is R1. Next one is non-inverting amplifier. Figure shows the diagram of non-inverting amplifier. If the signal is applied to the non-inverting input terminal and the feedback is given to the circuit, the circuit amplifies without inverting the input signal. Such a circuit is called non-inverting amplifier. It may be noted that it is also a negative feedback system, as output is fed back to the inverting input terminal. Now negative terminal held at V in. So current through R1 is IF equal to V in divided by R1 to left into ground. This current cannot come from operational amplifier input, so comes through R2 delivered from operational amplifier output. Voltage drop across R2 is IF into R2 equal to V in into R2 by R1, so that output is higher than negative input terminal by V in into R2 by R1. V out equal to V in plus V in into R2 by R1 equal to V in into 1 plus R2 by R1. Thus, gain is 1 plus R2 by R1 and is positive. Current is sourced from operational amplifier output in this example. Next one is summing amplifier. Figure shows the operational amplifier used as a summing amplifier circuit, much like the inverting amplifier but with two input voltages. In summing amplifier circuit, that is inverting input still held at virtual ground. I1 and I2 are added together to run through RF. So we get the inverted sum V out equal to minus RF into V1 by R1 plus V2 by R2. If R2 equal to R1, we get a sum proportional to V1 plus V2. It can have any number of summing inputs. We will make our digital to analog converter in this way. Next is differentiating amplifier. Figure shows the differentiating amplifier circuit. In this circuit, the non-inverting input is a simple voltage divider. Negative V node equal to V positive R2 divided by R1 plus R2. So IF equal to V negative minus V node by R1. V out equal to V node minus IF into R2 equal to V positive into 1 plus R2 by R1, R2 by R1 plus R2 minus V negative into R2 by R1. So V out equal to R2 by R1 into V positive minus V negative. Therefore, we get the difference V positive and V negative. Next one is differentiator. Two of the most fundamentally important mathematical operations are differentiation and integration. The operational amplifier can be used to perform either of these operations. A differentiator is a circuit whose output is proportional to the derivative of its input. The differentiator may be constructed from a basic inverting amplifier if an input resistor R is replaced by a capacitor C. Figure shows the differentiator circuit for a capacitor Q equal to CV. So I cap equal to dQ by dt equal to C into dV by dt. Thus V out equal to minus I cap into R equal to minus RC into dV by dt. So we have a differentiator or high pass filter. If signal is V0 sin omega t, V out equal to minus V0 RC omega into cos omega t. The omega dependence means higher frequencies amplified more. Next one is low pass filter. Low pass filter means integrator. The process of integration is complementary to that of the differentiation. A circuit in which the output voltage waveform is the integral of the input voltage waveform is the integrator. Such a circuit is obtained by using a basic inverting amplifier configuration with the feedback resistor RF is replaced by a capacitor C. If IF equal to V in by R, so C into dV by dt equal to V in by R. And since left side of capacitor is at virtual ground, minus dV out by dt equal to V in by RC. So V out equal to minus 1 by RC integration V in into dt, and therefore we have an integrator. It indicates that the output voltage is directly proportional to the time integral of the input voltage, and R1 into Cf is the time constant of the integrator. The gain of the integrator at low frequency can be limited to avoid the saturation problem if the feedback capacitor is shunted by a resistance RF. The parallel combination of RF into CF behaves like a practical capacitor which dissipates power unlike an ideal capacitor. For this reason, this circuit is also called a lossy integrator. The resistor RF limits the low frequency gain to minus Rf by R1, that is Rf equal to 10 into R1, and this provides DC stabilization. Next, the analysis of integrator, we can get A gain A equal to V0 by V1 equal to 1 by root of omega square into R1 square into C square plus R1 square by R square equal to R by R1 divided by root of 1 plus omega into Rf into Cf the whole square. At low frequencies, gain is constant at Rf by R1. Next, the operational amplifier is also used as a logarithmic amplifier. There are several applications of log and anti-log amplifier. Anti-log computation may require functions such as in x, log x, or sin hx. These can be performed continuously with logarithmic amplifiers. One would like to have direct dB display on voltmeter and spectrum analyzer. dB means decibel. Logarithmic amplifier can easily perform this function. Logarithmic amplifier can also be used to compress the dynamic range of signal. The anti-logarithmic amplifier is the input for the anti-log amplifier is fed into the temperature compensating voltage divider R2 and RTC and then to the base of Q2. The output V0 of the anti-log amplifier is fed back to the inverting input of A1 through the resistor R1. Another one application of operation amplifier is comparator. Comparator compares a signal voltage at one input of an operational amplifier with a known voltage called the reference voltage on the other input. In its simplest form, it is nothing more than an open loop operational amplifier with two analog inputs and a digital output. The output may be positive or negative saturation voltage depending on which input is the larger. Comparators are used in circuits such as digital interfacing, schemic triggers, discriminators, voltage levels, detectors and accelerators. Okay students, finally we have concluded the section. So thank you.